Okay, good morning, students. I welcome you all to the GATE class of analog circuits. So today we are going to see the introduction of op-amp, basic circuits, what we have inside op-amp, and we are going to start with the applications of op-amp too. We'll see some basic concepts and then we'll move on with the problems. Hope my screen is visible. So first, let us start with the introduction. What do you mean by this op-amp, operational amplifier? So operational amplifier, it is a basic amplifier. As you would have come across many amplifiers and devices and circuits itself. This is also an amplifier, but this amplifier can amplify both AC as well as DC signals, and this is also called a versatile IC, since this amplifier IC can be used not only for amplification but also for other mathematical, for performing some mathematical operations like addition, subtraction, differentiation, integration. All these things also can be done with this single IC, and that's why we call this particular IC as a versatile IC. Now if we go on with the background of IC, uh, it was originally uh, started with vacuum tube, and then from vacuum tube we went on with the invention of transistors, because when we were having vacuum tubes, it was um, very bulky. The size of the vacuum tube was very huge, and it occupied an entire room. We all know that. And then the size of the electronics, the size of the electronic components, it came down with the invention of transistor. And then the next technology is IC technology, integrated circuits technology. This even more shrunk the size of the electronic equipments and devices. And it even in IC we have an evolution, like it's not a single IC. Initially it was simply an integrated circuit technology, and then came very large scale integration, and then it was ultra large scale integration. That is, it means we are having more and more devices on a single chip. We started with few transistors in a single chip, and now we have billions and billions of transistors in a single chip. And that is the technological development in integrated circuits. What are the advantages of this IC? Why we are going in for this integrated circuit technology is, of course, as I was talking about the size plays a major role here. The very complicated, very huge circuit also can be brought into a single chip. So we'll have a very small size chip for performing a huge operation. So size is small, that is first advantage, and then cost is low because we are going in for batch processing, bulk processing. Power consumption will be less. It's highly reliable because we don't have any joints or something which will be left. No soldering, nothing is there. We are not giving any physical connection here, and therefore it is quite reliable. The operating speed is very high since the area of operation is very small. The signals will be transmitted at a the current and voltage, it will be flowing at a very faster rate, and therefore we'll have high operating speed here. Very easy to handle, of course, right? We all know that it is very convenient to handle an IC instead of giving a connection using discrete components. So this is only the major advantages. We can go on listing the advantages of IC. And this is the symbol of op-amp. Op-amp symbol, if you see, uh, it's a you can see the symbol. It's just a triangle where you have two inputs, non-inverting input and inverting input, and you have an output terminal. And of course, any device, if you want to operate, you need power supply for that as well. So you have two terminals for power. Plus 5 and minus 5 voltage is given here. Is actually we can give it as plus 15 and minus 15, also plus 15 minus 15 for a particular versatile op amp, which is IC741. So it is power supply will be given here, and then you can see, as I said, the versatile operational amplifier which is used is IC741. The pin diagram of IC741 is shown here. You can see you have a inverting. Let me take my pointer. So you can see you have a inverting terminal, a non-inverting terminal, and then power supply voltages, and then you have output terminal. You have two more pins, 1 and 5, which we will be calling it as offset null. 1 and 5 is offset null, that is in order to make the offset as 0. Okay, that is your offset null, right? And this is the package, how one IC will be packed. The circuit, operational amplifier circuit, is shown as an IC package. Here we have actually three major IC packages, like metal can package, dual inline package, and um, flat package. And the one which is shown here is a dual inline package, that too mini dual inline package. We call it as dip. This is mini dip. Okay, since you have only 8 terminals here, it is a mini dip. You could see, as I said, the same thing, two inputs, inverting and non-inverting input. You have two supply voltages, plus V and minus V, an output pin, two offset null pins, 1 and 5, and one you don't have any connection. See, eighth pin is left out as such. Now, very important, stages of op-amp. What is that you have inside an op-amp? We are seeing it as a symbol, right? What exactly we have inside this op-amp? What are the circuits we have? What operation it will do? To understand that, we should know what is inside an op-amp, right? So, the internal circuit diagram of op-amp is little complicated, and therefore, instead of seeing it as a circuit, we are going to see it as a block diagram. The overall op-amp internal circuit can be divided into four stages. The first stage is called as input stage, and then the intermediate stage, then the third stage is level shifting stage, and the last one is an output stage. So we'll see one by one. Right? So first one is input stage. Input stage, uh, we use dual input balanced output differential amplifiers here in this stage. The purpose of input stage is to provide high input impedance. Okay, because op-amp has a characteristics that it will provide high input impedance. So that characteristics comes from this input stage. Okay, so input stage we are using a differential amplifier. Differential amplifier characteristic is it will always provide a high input impedance, and therefore op-amp will also provide a high input impedance. Then comes the intermediate stage. Intermediate stage is again differential amplifier, but this time we are going to use dual input unbalanced output differential amplifier. Previous one is dual input balanced output differential amplifier. The next one is dual input unbalanced output differential amplifier. Okay. So the purpose of this differential amplifier again in the second stage is to increase the voltage gain. We all know one more important characteristic of a differential amplifier is it will provide high voltage gain. So in input stage itself, it satisfies two purposes. One is it provides high input impedance, and the second one is it will provide high voltage gain. Again, we have an intermediate stage. This stage is again a differential amplifier. The purpose of this is to increase the voltage gain as high as possible. Uh, and ideally the value goes to infinite. So when we talk about the ideal characteristics of an op-amp, we say that the ideal voltage gain of an op-amp is infinite. So that is achieved through this intermediate stage. So one stage of differential amplifier will just provide a high voltage gain. So when you have cascaded stages of differential amplifier, see here you will not have a single differential amplifier. It is cascaded stages of differential amplifier, multi-stage differential amplifier, and therefore the voltage gain is increased a lot. Okay, ideally, as I said, it is infinite. And third is level shifting stage, very important stage in this. This stage has been included here in order to satisfy two important criteria. One is this stage is responsible for producing zero output for a zero input. Of course, we all know that when I don't give any input, I'm supposed to, I'm not supposed to get any output, right? When my input is zero, my output also should be zero. So that is ensured at this stage. And the second one is the level will be shifted. That is, if you see, I in the introduction itself, I told that op-amp will amplify both AC as well as DC signals, is it not? So here you'll not block the DC. Generally, when you have multi-stage amplifier section, always we'll put a coupling capacitor. Okay, between the stages, we'll use a coupling capacitor which will be used to block DC, and only the AC signal will get amplified. Okay, so what will happen when I give an input here? my input will get amplified here, and then it will get amplified stage by stage in this intermediate stage. When my input is an AC signal, along with AC amplification, DC amplification also will be done here, because here we will not use any coupling capacitor between the differential amplifier stages. Got it? Generally, when you go in for a multi-stage amplifier, when you have cascaded stages of amplifier, in between every stage, we'll use a capacitor, which will be called as a coupling capacitor, in order to block the DC, right? But here in op-amp, here in this intermediate stage, we will not use any coupling capacitor, because we want to use op-amp for both AC and DC amplification. Okay, so we'll not use any coupling capacitor here, which will be blocking the DC. And therefore, what will happen when I give an AC signal? My AC signal will get amplified here, and along with that, a small amount of DC will also get amplified here. So what will happen when DC gets amplified? From where we will be getting the DC first? I'm giving an AC signal here, but still, you all know that for an op-amp, we are providing the DC biasing voltage, that is plus 15 and minus 15. We don't know V plus and V minus. So it is a DC bias voltage. So this bias voltage will be there inside the circuit. Okay, and this small amount of DC voltage will also get amplified in this intermediate stage, because this is a high gain amplifier, is it not? So even a small bias current which is there inside the circuit will get amplified. So along with the AC, the DC will also get amplified here. So what will happen? My AC signal will get shifted by a DC level. Okay, so original signal, AC signal, it will get amplified. Along with that, you will be having a DC shift also here. So I want to bring back the DC to zero. Okay, so that is what this level shifting stage will do. So whatever value it has been shifted, this stage will bring it back to the normal level. Okay, so that is your DC will be made zero, and you'll have only the AC amplification here. So that is taken care by a level shifting stage. Okay, so it will also act as a buffer. The second purpose is, there are two purposes here. One is zero output for zero input, and this is achieved by level shifting. The second one is, it will act as a buffer, in the sense you cannot directly connect an intermediate stage to the output stage, since this is a differential amplifier stage. The output cannot be directly connected to here, to this output stage. We need a buffer in between, which will be a level shifting stage, which is usually an emitter follower. Generally, this third stage is an emitter follower stage. Okay, so this is in order to uh, connect uh, the intermediate stage with the output stage. So this will act as a buffer in between. Okay, and finally, the output stage. Again, output stage also has two purposes. One is, it has to provide low output impedance, and the second one is, it has to provide a symmetrical swing. Okay, this is achieved by complementary symmetry push-pull amplifiers. Got it? So I just repeat, every stage has two purpose. Okay, first stage, input stage, is a dual input balanced output differential amplifier, which is there in order to give high input impedance and high voltage gain. Second stage, intermediate stage, here we'll have dual input unbalanced output differential amplifier, cascaded stages. This is in order to improve the voltage gain to a very high level, and all these cascaded stages will not have any coupling capacitor, and therefore both AC and DC will get amplified at this stage. Third is a level shifting stage, which is an emitter follower. This again will produce, it is there for two purposes. One, it will act as a buffer in order to connect the intermediate stage with the output stage, and the other one is, it will produce zero output for zero input by bringing down the DC to zero level. Okay, and finally the output stage, this is complementary symmetry push pull amplifier, which is there in order to uh, provide a low output impedance and a symmetrical swing. That is, the sinusoidal signal, whatever AC signal we are applying here, will be made symmetrical. The positive half and negative half will swing, will be symmetrical using this stage, because of this stage. Okay, so these are the circuits we'll be having inside the op amp. Right? Now, again, a very important topic, ideal characteristics of op amp. Right? What is this op amp characteristics if we see? We have um, actually two types of characteristics, ideal and non-ideal characteristics, DC and AC characteristics. Like that, we can define the characteristics of an op-amp in different ways. And this is an ideal op-amp is supposed to have these characteristics. Practically, it will not happen. Ideally, it should have these characteristics. What are the characteristics if you see? The first and foremost one is infinite uh, gain. Okay, infinite open loop gain. So infinite open loop gain means, just imagine what is the gain? It is output by input, right? So output by input is equal to an infinite value, which is providing very high gain, which is equal to infinity, right? So infinity gain amplifier. Okay. So output by input is equal to infinity means when it will become infinity, when your input is zero. Output divided by zero only will give you an answer as infinity, right? So it means your differential input is zero. Input is not a single input. We saw no in the symbol of an op-amp, always op-amp will have two inputs, right? One is inverting input and the other one is non-inverting input, right? So the difference between these two will go as an input inside the op-amp. Okay, so that differential input will be zero, and therefore only we were able to achieve this infinite open loop gain. Okay, and then high input impedance, of course we are using a differential amplifier in the input stage, no? So your input impedance will be infinite. Ideally speaking, it should be infinite. Practically, this will be very high. Similarly, gain will be very high in the order of 10 to the power of 6. Okay, but ideally speaking, it is infinity. Similarly, input impedance, it is very high for an op amp practically, but ideally speaking, that also should be infinity. Output impedance is zero, ideally speaking, but practically it will be very low. If you're why what is the advantage of having a low output impedance? That's why we used stage 4 output stage in the op amp. Complementary symmetry push pull amplifier, the main purpose is to provide a low output impedance. No, what is the purpose of low output impedance? Any guess? When you have low output impedance, many load can be connected to the circuit without any loading effect. Okay, so you can connect any number of loads to this op amp circuit, you will not have loading problem. Okay, so that is the advantage here. Bandwidth is infinite from f is equal to 0 to f is equal to infinity. I'll have a constant gain, so it is infinite bandwidth. Zero offset, there will not be any offset voltage. It means when my input is 0, output will be 0. Offset is made 0 here. And CMRR is very high. It is infinity. Ideally speaking, it is infinity. CMRR is common mode rejection ratio, which is differential gain by common gain. Okay. So this CMRR ratio will also be infinity for an op amp. Okay. So these are ideal characteristics. But practically, when we try to do this, we will not get exact ideal characteristics. You can see here. Input impedance, ideally it is infinity, but practically speaking, input impedance will be in the order of 10 power 6 to 10 power 12. Okay, and then output resistance should be ideally 0, but it will be of 100 to 1000 ohms. Gain should be infinity, but it will be between 10 power 5 to 10 power 9. It depends because we have two types of op amp, transistor based op amp and FET based op amp. So you'll have a change in the characteristics. Similarly, bandwidth, everything. Okay, everything is, you ideally speaking, whatever, if it is infinity, it will be very high practically. Ideally, if it is 0, practically it will be very low. Okay. Now, very important rule of op amp, the golden rules of op amp. It means we have two important rules. One is always we'll consider the differential input to be 0. Okay, the circuit, whatever input you give, you have two inputs here, no? Input V plus and V minus. Whatever value I give here and here, it the nature of op amp is it will adjust such that it will bring the voltage at the non-inverting terminal and inverting terminal to be equal. That is the difference between these two input as 0. Then only output, the gain of this op amp will be infinity. Is it not? He said gain is infinity. V naught gain is equal to output by input. So it means it will be equal to infinity only when input is 0. So when your differential input is 0, when your differential input will be 0, when both the values are same. Okay. So Whatever input we give here, the op amp will try to make the potential at non-inverting terminal and inverting terminal to be same, and therefore the differential input is 0. Okay. Second one, since it is having high input impedance, no current will enter into the op amp. See, you are connecting some circuits here and all, means some current is flowing from the source, means that current, it will not enter into the op amp. If you have a branch here, it will, the entire current will flow through the other branch. Nothing will enter into the op amp. Okay. So remember these two golden rules of op amp. Since it has very high input impedance, no current will enter into the op amp. Since it is having high gain, that is infinite gain, it means your differential input is 0. So with these two rules only, we are going to analyze all the op amp circuits. So whenever you're doing analysis of an op amp circuit, applying these two golden rules only, we'll simplify and we'll try to understand what exactly that circuit is going to do. Okay. First is inverting amplifier. Okay. We are going to see about an inverting amplifier. Right. So this is the inverting amplifier circuit. It means input is given to the inverting terminal, non-inverting terminal is grounded, and you are having a feedback here, okay, from the output to the input. So when you are connecting a circuit like this is called as inverting amplifier. Okay. And we'll try to get an expression for this inverting amplifier. So for that, I'm going to write expression for this current. See, the current that is flowing here, the same current is flowing here also. First, I'm writing the equation for this current I1 with respect to Vi. So I1, it is the current flowing in this branch. So the voltage difference is Vi minus 0 divided by the resistor R1. And therefore, it is Vi by R1. Similarly, the same current, we know no current will enter into the op amp. So whatever I1 current is produced, I mean it is coming from this source, it cannot enter into the op amp, and therefore the entire current will flow here. I said no, we have to always remember the golden rule, right? So no current will enter into the op amp. So when I'm doing the analysis, I assume that whatever I1 is coming from the source, the same current will flow through this feedback path also, since it cannot enter this op amp. Okay. And therefore the I1 can, or the current I1 can also be written with respect to the voltage or output voltage V0. So I1 is equal to the 0 minus V0 divided by R2. Okay, so it is minus V0 by R2. So one more thing I didn't ask you, how come this value has been written as 0? The voltage at this point has been taken as 0. Any guess why this particular voltage is 0? The voltage at this node is 0. The golden rule of op amp, right? The second golden, I mean, the first golden rule of op amp. We say always the potential difference between these two terminals is 0. It means the potential at the inverting terminal and the potential at non-inverting terminal both are same, right? If you see, non-inverting terminal is grounded here, is it not? And therefore the voltage at this point is 0. So it means the op amp will try to make the voltage at this point also 0. Okay, so that is why we have considered 0 here. So I1 is written as Vi by R1, and I1 is also written as minus V0 by R2. Both are I1. So we equate these two and rearrange. From that we can say that V0 by Vi, the gain is equal to minus R2 by R1. So gain of an inverting amplifier is minus R2 by R1. Okay. Next. So the one what we saw now is inverting amplifier. Okay. So input was given in the inverting terminal of the op amp. Now we are going to see non-inverting amplifier. Okay. Now you can see the circuit. This is the circuit of a non-inverting amplifier. Now I am giving the input to the non-inverting terminal of the op amp, and inverting terminal is grounded through a resistor. Of course, you have a feedback here too. Okay, this type of circuit we call it as non-inverting amplifier. So now let us try to write equation for this also, and try to get the output expression, gain expression for this. Okay, same way whatever we did there, the similar thing we have to do here also. Okay, we are again talking about this potential. What is the voltage at this point? Okay, So same expressions now. Whatever voltage, we'll find out what is the voltage at this point. You can see that output total voltage is here, and you can see a voltage divider circuit here, right? And therefore we can say that the voltage at this point will be equal to the total voltage V naught into Rs divided by Rf plus Rs. I'm applying voltage divider rule. You have a total voltage and it is coming here. You have a resistor Rf, and from here resistor Rs to this one. So if I want to measure the potential from this point to ground, it is total voltage into Rs divided by Rf plus Rs. So that is what the voltage at this point. Okay, from this you can rearrange and say that V naught is equal to Rs plus Rf by Rs into this voltage Vg. Okay, because this voltage is Vg, the voltage across this resistor is Vg. The voltage at this point is also can be taken as Vg. Okay, so that is what applied here. So comparing these two, we can find out that V naught is equal to 1 plus Rf by Rs into Vg. So this is output is equal to gain times the input Vg. So it means the gain of non-inverting amplifier is 1 plus Rf by Rs. Understood? Previous one what we said? The gain of an inverting amplifier is minus R2 by R1. That is minus uh, the feedback resistance divided by the input resistance. That was the gain of inverting amplifier. Gain of non-inverting amplifier is 1 plus Rf by Rs into Vg. Okay. And this is a voltage follower. We are just seeing the basic circuits of op-amp. So first one was inverting amplifier, second one is non-inverting amplifier, and now we are seeing a very important one, which is voltage follower. Very simple and important circuit, which is voltage follower. As the name indicates, voltage follower means output voltage is equal to input voltage. Voltage is followed. Whatever is my input voltage, the same will be the output voltage. Output follows the inputs. That's why we call this as a voltage follower. Okay, you can see no resistors, no capacitance, nothing is there in the circuit. Just you have a feedback from the output to the input. Input is given here, and from the output you have a feedback to the inverting terminal. Okay. So here output V out will be equal to the input V in. Then what is the purpose of this? Any guess? When output is equal to input, what is the purpose of this voltage follower? Yes, that means it is used for impedance matching. It will just act as a buffer. Okay, it will match the impedance of the previous circuit with this next circuit, because this will have high input impedance, no resistor is used, and therefore high input impedance, low output impedance, and therefore you can match any source with any load through this voltage follower circuit. Okay, so this will be used as an impedance matcher. Okay, the next one is a summing amplifier. Now we are slowly entering into the applications of op-amp. Okay, so first we saw what is the op-amp, what your circuits you have inside an op-amp, and then what are the characteristics of an op-amp, basic circuits of op-amp, inverting, non-inverting, and voltage follower. And now we are entering into the applications of op-amp. We said no, this is a versatile IC which can be used for mathematical operations also, right? So now we are going to see how this could be used for mathematical operation. So first, adder. Okay, when you want to add two voltages, you can use a op-amp to construct a summing amplifier. Okay, and this is how your summing amplifier will look like. Actually, you have two types of summing amplifier: inverting and non-inverting. So you have inverting summer, non-inverting summer, or even I can call it as inverting adder or non-inverting adder. Okay, so now this is an inverting adder circuit. But see, multiple inputs are given to the inverting terminal and non-inverting is grounded, and you have a feedback as usual. So when you try to write equation for this, just make a try. How will you write equations for this? Again, you have to apply the golden rules. Since non-inverting terminal is grounded, this voltage is 0 means this voltage is also 0. So with this, you have to just find out expression for this. Okay, write equations for this and compare it with the output expression, rearrange and try to get this expression. Just make a try. Same way you have to write equation. This voltage is 0, so therefore this voltage is also 0. Write KVL equation for this as well as this current flowing into and out of this node. Okay, this is our node voltage is 0. Current flowing into this node and out of this node. Write an expression for this. Just try to simplify and get an expression. Anyway, output has been shown here. Output expression. Just make a try. I'll just give you 1 minute time. Let's hope you have got this expression. Right? Any doubts? It was very easy to get it, right? So output is equal to what you can see here. Output is equal to uh, some weighing factor is there, minus RF by R1 times the input plus RF by R2 times the input, like that. Anyhow, it is the sum of the input. Suppose if you make all these resistor values as equal, R1, R2, R3, whatever you have here, if all these resistor values are equal, then you can say that V out is equal to minus RF by common R. Okay, RF by R, which will be the weighing factor, into V1 plus V2 plus something. Okay, so sum of inputs into a gain. So that is an inverting adder. So this is how shown. You can see same circuit. Okay, this is what I asked you to write. You'll have equation for this current I1, I2, I3. All these things are flowing into the circuit, and I4 is flowing out of the circuit. So total current flowing into the circuit and out of the circuit are equal. Write equations for this all these currents. When you equate, you'll get this expression, right? That's what I said. It's very simple, right? Hope you all got this. Any doubt? If you have doubt, you can see this. Still having any doubt? Just you have to write the current equations, equate. I mean, you have to write KCL, right? And if all the resistor values are equal, I said no, then it is output will be equal to gain times the sum of input. That RF by R will act as gain. Okay, and since you are giving all the inputs in the inverting terminal, you'll get that minus sign, obviously, right? A similar way, you have non-inverting summer too. Okay, so non-inverting summer, I'm providing inputs in the non-inverting terminal, multiple inputs in here. Only two inputs are shown. If you want, you can give 3 or 4 inputs also. All the inputs are given to the non-inverting terminal. Inverting terminal is grounded, and you have a feedback path here, right? So again, you have to write equation for this node. Okay, find out what is the voltage at this point. Once you find what is the voltage at this point, how the circuit will look like, you can omit this part. Okay, because with the uh, help of this V1, R1, V2, R2 only, you are finding out what is V plus. Once V plus is found, this circuit will look like a non-inverting amplifier, because input provided to the non-inverting terminal, you have a resistor to ground here, and you have a feedback. So it is the non-inverting amplifier. So once V plus is found, I can say that output is equal to 1 plus RF by RS times the input. So directly I'll get the expression, no? Just try this also. First, how will you find the input here, V plus? How will you find what is the voltage at this point? Superposition theorem, because you have two inputs here, no? You have to consider one input at a time. Consider V1 find out what is the output. Consider V2, find out what is the output. When you are considering V1, V2 will be grounded. When you consider V2, V1 will be grounded. Okay. So just make a try. Anyway, I'm showing it here. Now first we are considering only V1. See, V2 is grounded here. Understood? V1 is considered, V2 is grounded here. And therefore, find out the output here. What is the value of V plus? Just voltage divider rule. Similarly, consider V2, remove this V1, find out what is the voltage here and add both. That will be V plus. See, considering only V2, this is the output. So V out will be equal to both V out 1 plus V out 2. Both will be combined. Okay, and this is out. So V out is equal to 1 plus RF by RS times the input. Okay, the sum of the inputs. And here again, if all the resistor values are equal only, you'll get this. This R2, R1, R2, if all this R1, R2 are equal, all the resistors are equal, again I can say output is some gain times the sum of the inputs. Now this gain is non-inverting amplifier gain, because this is a non-inverting adder. It is a non-inverting amplifier gain. Okay. Okay, so now we have seen few applications, right? The adder applications. Let's try with the problems, right? Very simple problem. Determine the output voltage for the following circuit. First, see, whenever a circuit is given and they are asking to find out what is the output of the circuit, how will you do the problem? First, you have to uh, identify what type of circuit is this. Okay, so what type of circuit is this? How will you identify? When you have multiple inputs in the same terminal, it is a adder circuit. So you have two inputs in the inverting terminal and therefore it is an adder circuit. So after identifying the circuit, you should try to evaluate what is the output for this. So this is an inverting adder circuit. So because two inputs are given in the inverting terminal of the op amp, now try to write expression. We know that output expression of an inverting amplifier, just now we derived, output is equal to minus RF by R1 times the first input. Similarly, minus RF by R2 times the second input. So that is what written here. And all RF, R1, R2, everything, if you substitute, you'll be getting the answer is minus 19 volts. Just make a try, see whether you are getting this. Very simple direct problem. Very, very simple problem. Since we are starting with the concept now only, I've given a basic problem here. Right? 10k divided by 2k into 3 volts plus 10k divided by 5k into 2 volts. So you'll be getting the answer is minus 19 volts. Hope there is no doubt in this, right? Yes. Understood? Shall I move to the next problem? Yes, next one. Find the output expression. See again, it's not a single circuit. You could see some set of circuits are here, and finally we need to produce the output. What did I tell you? Always first we have to identify what circuit is this. Generally, it is possible to write expression, is it not? So we can split this circuit into two. Since you have two op amps, first we'll see what is the circuit around op amp 1 and then what is the circuit around op amp 2. Op amp 1, if you see, where is the input given? Input is given to the inverting terminal, non-inverting terminal grounded, and you have a feedback. So of course, then what is the circuit is? Easily we can identify this as a inverting amplifier circuit, right? And then, so I can easily find out what is the output here. Since it is inverting amplifier, output is minus RF by RI times the input. Easily I can get what is the output at this point, right? Now, second one. Now, this is the second op amp. You can see it has an input here. The output of first circuit is the input of the second one, and one more input is also given through a resistor to the same terminal. I already told, is it not, when you have multiple inputs to a same terminal, to the same terminal, either to inverting or non-inverting, it means it is a adder circuit. So you have two inputs directly given to the inverting terminal of the op amp, and therefore this is an inverting adder circuit. Non-inverting grounded, you have a feedback. See, so this is an inverting adder. So just for seeing only the circuit is big. When you try to identify what type of circuit is this is very simple. We know how to write the output for an inverting adder, is it not? Just now we saw. So just make a try. I'll give you 1 minute time. Make a try. Try to find out the answer for this problem. It was very simple. I've given you the logic. Try to find the output for this. Yes. Make it fast. Anyway, I'll show you the answer. Just make a try. First one, inverting amplifier. Second is inverting adder. Inverting amplifier is output is equal to minus R2 by R1 times the input. So you will get what is V01. So with V01 and V2 as the two inputs to this adder, it is minus 20k by 10k into V01 plus minus 20k by 10k into V02. Right? So your output will be, this is 20k by 10k. What will you get? First output V01 output will be minus R2 by R1 times the input. Okay. So R2 by R1 is 20 divided by 10. It is 2. So 2V1 will be your input. And here it is V2. So this V1, since we don't know what is the value of V1, your expression will be in terms of V1 and V2 only. Okay. See, V2 is here. That value is also not known. V1 is here. This value is all the resistor values have been given. That is why you are getting an expression here. Okay, so V01 is minus R2 by R1 times V1, this is this. And V0 is the other resistors, minus R5 by R3 into V01 minus R5 by R4 into V2. So when you simplify your expression is 2V1 minus V2. Okay, 2 times 2 into V1 minus V2. That is your output expression. Depends on V1 and V2 values, you'll be getting the final expression. Right? If V1 and V2 were given directly, we can given straightforward output value. Okay. Hope there is no doubt in this. Shall I move to the next one? Understood? All steps have been shown clearly here. Hope there is no doubt. Now again, you have to find what is the output V0 here. A circuit has been given here, and for this circuit, you have to identify, find V0. Okay, first find what is the output voltage here. In one more condition is given, you have to verify if R3 by R4 is equal to, this got cut here. Actually, if R3 by R4 is equal to R1 by R2, R3 by R4 is this. Okay, R3 by R4 is equal to R1 by R2. Then the circuit is an instrumentation amplifier with gain 1 plus R2 by R1. Okay, so if these two resistor ratios are equal, we have to prove the given circuit will act as an instrumentation amplifier. So how will you prove a circuit will act as an instrumentation amplifier? It has to satisfy the expression of an instrumentation amplifier. The gain of the instrumentation amplifier is 1 plus R2 by R1. So output should be this much times the input. Okay. And of course, if it is a instrumentation amplifier, it has to satisfy the differential amplifier characteristics. Okay. First, let us find out what is the output expression for V0, and then after getting the expression for V0, we will substitute the condition what is given here and see whether we are getting an instrumentation amplifier, right? So for that, first you have to find out what is V0. As I said, what is the procedure? In order to find the output of any circuit, first identify what circuit is this. Here again you don't have a single op-amp circuit. You have an op-amp here, a circuit for that, and an op-amp here, and you have a circuit here, right? So we'll go one by one. First, take this op-amp. Input is given to the non-inverting terminal. Inverting terminal is grounded through a resistor, and you have a feedback. Of course, it's a known circuit, is it not? What circuit is this? It is an inverting amplifier circuit. Okay. So inverting amplifier circuit is there. We know what is the output expression. Output will be always 1 plus Rf by R1 times the input. So 1 plus R3 by R4 times the input V1. That will be V01. Okay. And now what is this circuit? You have an input to the non-inverting terminal, you have an input to the inverting terminal, and you have a feedback. So when you have input to both the terminals, non-inverting and inverting terminal, your circuit will be either a differential amplifier or a subtractor. Okay, a differential amplifier means you'll have different resistors used. If all the resistor values are equal, then it will act as a subtractor. Okay, so anyhow, it is going to be a either a differential amplifier or a subtractor circuit. We'll just find out or try to get an expression for this. See, first part is a non-inverting amplifier, and therefore output is 1 plus R3 by R4 times the input. Now this will act as the input to the second part of the circuit, which is you have, and so the entire circuit now I'm simplifying. After finding V01, I'm simplifying the circuit like this. See, you have an input here as well as you have an input here. Since you have two inputs, you have to consider one input at a time. By applying superposition theorem, consider V01, find out what is the output. Consider V2 alone and find out the output. So when you apply this, you will be getting, when I consider V01 alone, it means V2 is grounded. It looks like an inverting amplifier. See, this is grounded and you have an input applied through a resistor to the inverting terminal and you have a feedback. So it is a inverting amplifier and therefore output will be equal to minus R2 by R1 times the input. So that is what written here, minus R2 by R1 times the input. So this is the output when you consider V01 alone, and output will be equal to 1 plus, that is when I consider V2 alone and I'll make V01 as grounded, this will look like a non-inverting amplifier. Input applied to the non-inverting terminal, inverting is grounded through a resistor, feedback. So output of a non-inverting amplifier is 1 plus Rf by Ri times the input. So 1 plus R2 by R1 times the input. Okay. So you can simplify this and we have an assumption here, no, R3 by R4 is equal to R1 by R2. So apply that. Okay. So wherever you have this R3 by R4, you can change it as R2 by R1 by R2. So when R3 by R4 is equal to R1 by R2, what will happen? See, this R3 by R4 will be R1 by R2. So R1 by R2 here, here R2 by R1. Okay. So this will get cancelled. Okay, one term will get cancelled and this is remaining left out. So when you see that your output is equal to 1 plus R2 by R1 times the differential input. That is what a differential amplifier or an instrumentation amplifier is, it not? Output is 1 plus R2 by R1 times the differential input V2 minus V1. So this acts as an instrumentation amplifier. Got it? This is how we have to solve a problem. So whenever they ask you what is the output of the given circuit, what is the procedure, you have to first identify what type of circuit is that. Okay. If it is a single circuit, you can identify as such. If you have multiple op-amps in that circuit, split the circuit into smaller circuits around each op-amp. Identify what type of circuit is that, and then if it is a known circuit, directly try to write the output expression. If not, apply KVL or KCL or apply the golden rules of op-amp. Simplify and try to get the expression of an op-amp. Okay. So hope you understood this one. Now differential amplifier. Okay. Different, just now I was talking about differential amplifier, no, when you have two inputs given to a single circuit. Okay, single op amp. See, V1 is applied to the inverting terminal of the op amp and V2 is applied to non-inverting terminal of the op amp. Suppose both V1 and V2 are applied to the inverting terminal of the op amp itself, then it will act as an inverting adder. If both V1 and V2 are applied to the non-inverting terminal of the op amp, then it will act as a non-inverting adder. Since both are applied at different terminals of the op-amp, this will act as a differential amplifier, or with further simplification, this can be made as a subtractor also. Okay, so your circuit will look like this. Of course, as usual, you have a feedback here from the output to the input. And we are going to apply the golden rule to simplify this differential amplifier, to analyze this differential amplifier. What is that golden rule? Whatever voltage I have in the non-inverting terminal of the op-amp, the same voltage will exist in the inverting terminal of the op-amp also. It means V plus will be equal to V minus. So let me get an expression for V plus. Let me get an expression for V minus. I shall equate these two, right? So first I'm trying for the current I1, okay, and the same current flows here. So from that I'm identifying what is V plus. V plus and V minus equating, okay, both are equated. Simplify, you're getting an expression V naught is equal to R2 by R1 times V2 minus V1, okay. R2 by this and this term will get cancelled here, okay, and what is left out is R2 by R1 times V2 minus V1, okay. So output is R2 by R1 times the difference between the inputs. So that is why we call this a differential amplifier. The difference between the inputs is amplified by a factor of R2 by R1. If suppose in the same differential amplifier, this is my R2, this and this is R2, and this is R1, is it not? If I make all the resistor values are equal, this is R, this is R, this is R, and this is also R. What will happen in this expression? Both R1 and R2 both will be equal. R by R, it will get cancelled. So output will be V0 is equal to V2 minus V1. So it is the difference between the two inputs. It means it is a subtractor. You're just subtracting the voltage V2 and voltage V1. V1 from V2. Okay. We are getting the expression here as V2 minus V1. What should I do if I want V1 minus V2? What change should I make here? See, this is basically a differential amplifier circuit, and therefore output is equal to gain times the difference between the input. If all my resistor values are equal in a differential amplifier, my circuit will behave as a subtractor. Output is equal to one input minus the other input. Okay, and which input comes first, which input comes next, that depends on, that is what I'm asking now. If I want V1 minus V2, what is the change I have to make here? This is how your questions will be. Okay, so if V1 minus V2 means what should be changed? Just change the inputs here. Okay, give V2 here and V1 here. That is, V1 will be to the non-inverting terminal and V2 will be to the inverting terminal. So automatically a final expression will be V1 minus V2. Okay, understood? Okay. So next application of op-amp is integrator. Okay. How to use op-amp as an integrator? So op-amp can be made used as an integrator by connecting a capacitor in the feedback path. So this is my feedback path. You can see usually the circuit, whatever we have seen till now, the inverting amplifier, non-inverting amplifier, uh, the previous circuits, whatever we have seen till now. Okay, so everything, it had a resistor here, adder circuit or a subtractor circuit, differential amplifier circuit, whatever it is. Always we had a resistor here in the feedback. Okay, now for the first time we are seeing a circuit with a capacitor in the feedback. Whenever you have a capacitor in the feedback, that circuit will act as a integrator. Okay, so you could see rest all the same. See, this is input is applied to the inverting terminal of the op amp, non-inverting is grounded. If you had, if at all you had a resistor here, this is a normal inverting amplifier circuit. That resistor is replaced by a capacitor, and therefore now this entire circuit will act as an integrator, right? So try to write expression for this. Again, we'll be applying the golden rules. Okay, the current, we are calculating the current at this node. Okay, we are writing equation for this node, nodal equation. Since this voltage is 0, by golden rule, the voltage at this node is also 0. So the total nodal voltage is equal to 0 means write the expression for the current that is flowing into the node and the current that is flowing out of the node. Okay, total current is equal to 0. Write expression for that current through the capacitor, current through the resistor, equate it. So this is current through capacitor and this is the current through the resistor. Equate both IF and this IS. So rearranging, you'll get output is equal to minus 1 by RS CF times the integration of the input. Can you see this now? Output is integration of input by a factor 1 by RSCF by an integration factor. Okay. And what is the application of this integrator? There are two major applications. Okay, integrator is used in many of the circuits. Okay, but major application is it can be used to generate a ramp signal. Okay, when you give a constant voltage, you'll be getting a ramp voltage at the output of the integrator. So whenever you want to generate a ramp signal, you can use an integrated circuit. Okay, and then whenever you want to generate a triangular wave, that can be generated by giving a square input to your integrated circuit. It means to an integrated circuit, when I give square wave as an input, my output will be a triangular wave. So when you want to generate some waveforms, okay, triangular waveforms, then I can use an integrator to generate it. Okay, so both ramp and triangle, mostly it will be used in waveform generator, timing circuits and all. Okay. Similarly, differentiator. Differentiator will, I think it's almost time. So we'll see this differentiator and we'll end up here. Differentiator, same thing, capacitor will not be there in the feedback, instead capacitor will be in the input side of the op amp. Okay, so instead of input resistor, you'll have an input capacitor. Again, apply the golden rules of op amp, try to get an expression, the current flowing through this capacitor and the current flowing through the feedback resistor, write equation for this, and this both will be equal. So this equal to this, write equation, rearrange, you'll get output is equal to minus RFCS times differentiation of input voltage. This is my input voltage, no? Differentiation of input voltage. So output is differentiation of input voltage. Of course, some constant times, which will be the gain, right? And what is the application here? The main application of a differentiator is edge detection. Okay, whenever you are using a square wave as an input to some circuit and you want to see when it changes from high to low and low to high, the edges of the square wave, then the transitions, when the transition occurs from a positive value to the negative value or from negative to positive, when you want to find out this, we'll be using a differentiator circuit. It will find the edges. Okay, so you can give a square wave input to the differentiator circuit and you can see what is the output. The output will be spikes as it is shown here. For a differentiator circuit, what is shown here, if my input is a square wave, the output will be spikes as you have here. Okay. For this, I'll get a negative spike here. For this negative waveform, I'll get a positive spike here. Like this, we'll be getting the spikes. It means which is detecting the transition from high to low and low to high. Okay? So this is a differentiator. Hope you have understood till this. So we have started with the basics and we are entering into the applications of op amp. We have seen inverting and non-inverting amplifiers, inverting and non-inverting adder, and then a differential amplifier, then differentiator, integrator, so many applications we have seen. Okay. Still we need to see comparators, limit trigger, all those things. So that we'll be seeing in the next class and we'll move on with more of problems. Okay, so now we have almost understood the basic concepts of op amp. Okay, how to analyze a circuit, how to find the output expression of a circuit, what are the assumptions we have to make, all those things hope you have understood. So with this, we'll be going on with more problems in the next class. Any doubts? In this, we'll stop here. We'll conclude today's gate class here. And we'll continue in the next class. Any doubts? No? Okay, so then we'll conclude here. Thank you, students. Thanks for your patience.